Okay. Okay, so today we keep on talking about the premix flame structure. Okay, so I've drawn this very rapidly. Okay, the full structure. So we have a preheat zone and a reaction zone. Okay, and we've seen that these two zones have a characteristic length. Okay, a diffusive length of the preheat zone, which we're going to call LD, and a reaction zone, which is typically a much thinner, okay, reaction zone. Okay, all throughout the course we have said how the characteristic high activation energy, okay, combustion reactions are actually characterized by extremely fast, okay, reactions, or alternatively, flames are characterized by being extremely thin. Okay, you probably see me now. Can we estimate the ratio of the reaction layer length, okay, to the diffusion or preheat length or thickness? So this ratio here, LR over LD, okay? Now, we can, by adopting a sort of a simplified approach. So first of all, consider the definition of this temperature Ti. So what is Ti? Ti is the temperature at the boundary, okay, between the preheat zone and the reaction zone. Okay, so at the boundary of these two, so the boundary value of temperature is this Ti. Ti is called the ignition temperature. Okay, and it's essentially a temperature where you have to think the reaction rate starts becoming non-zero. So for smaller values of temperature here in the preheat zone, by definition, the temperature is too low, okay, to be of any value, so that the reaction rate is of any value. So the reaction rate is essentially zero. So we'll just write down the reaction rate is here is zero, whereas here it's different from zero. And you know that because of the high activation energy, this is a very important property of the exponential dependence on temperature of the Arrhenius reaction rate. We know that the reaction rate is essentially delivered, okay, only for temperatures which are very close to the maximum temperature, which is say in this case, the adiabatic flame temperature. So Ti is very close to, we expect it to be very close to Tb, okay? Smaller than Tb, but close to Tb, okay? So one assumption that we can certainly make, okay, is that the difference, okay, between, for example, Ti and Tu, okay, the variation of temperature in the preheat zone, you can fairly or safely regard it as Tb minus Tu, okay? And this is because essentially Ti is very close to Tb, as we said over here, okay? So that's one assumption, okay? Okay, so how can we estimate these the ratio of these two length scales? One thing that we can do, for example, is enforce the continuity, okay, of heat fluxes, okay, conductive heat fluxes, okay, at the boundary between the preheat and the reaction zone. Okay, so you can write this as the following: the slope, okay, of the temperature, so the dt by dx calculated, let's say, in the reaction layer, Lr, must be equal to, okay, for continuity of fluxes, to the dt by dx in the preheat zone. Okay, so essentially we're looking at this profile here. Okay, TB, this is TI, and this is TU. Okay, so how do we estimate these gradients, okay, of temperature? Well, dt by dx calculated in the reaction zone, okay, can be sort of estimated as roughly as TB minus TI, so this difference here, divided by LR, right? On the other hand, you're following, right?
Sí, sí.
Okay. The gradient estimated in the preheat zone, which can be written as Ti minus Tu here, divided by, so this is LD and this is LR, okay? So this is divided by LD, can be approximated, as we said, because the ignition temperature is very close to the final, okay, maximum temperature. The adiabatic flame temperature can be estimated as TB minus TU divided by LD. Okay. Okay, that's all very good, but what do we know about these two gradients? Well, we know TB and TU, because essentially these are thermodynamic. Well, TU is essentially a boundary condition. Okay, it's a given fact. Okay, it's the temperature of the incoming mixture. TB can be calculated from equilibrium. Okay, or simply by adding to TU. Okay, the heat of reaction divided by Cp. Okay, QC over Cp. What about Ti? In fact, what about the difference between TB and Ti? Well, this we don't really know. So in this expression here, there are a few tricks that you can use in these very simplified, sort of highly simplified analyses. For example, suppose I want to write the reaction rate, okay, as a Taylor series, okay, about the temperature TB. So how would I write this? Okay, regardless of the fact that I'm not using the explicit form, the exponential form of the reaction rate, I'm just writing down the expression as the expansion, okay, in a Taylor series about this point here, which is the highest temperature TB. So I will just have to add essentially a higher order term, which is the derivative, d omega by dt, calculated in TB, and then the delta T, which is essentially T minus TB, okay? Plus, let's say, higher order terms. Now, why am I doing this? Because I'm supposing, okay, to be near TB, so that the higher order terms are negligible, okay? So when you're near the value of TB, things like T minus TB squared, squared or higher, they're very small, okay? So you can neglect them. Okay, and remember that Ti, the ignition temperature, is very close to Tb. Okay, and so we can use this to actually solve for Tb minus Ti. So I just substitute here for T, Ti, okay, and here. And we have an expression, well, let me just write down approximately equal to omega Tb, so the rate of reaction calculated at the maximum temperature, minus the rate of reaction at the ignition temperature, okay, divided by the derivative d omega by dt calculated at Tb. Okay. Now there's another approximation that I can make, because remember that, and this is quite crucial, remember that the reaction rate starts, okay, at the ignition temperature and finishes at the adiabatic flame temperature, okay? And remember that for temperatures lower than the ignition temperature, the reaction rate is 0, okay? So we can say essentially that the ignition temperature is the last temperature for which we can assume, okay, that the reaction rate calculated at the ignition temperature is still 0, okay? Because Ti is, well, you can write it yourself, is the first temperature for which we can say that omega starts being non-zero, okay? Remember that, again, I have to stress this many times, okay? The exponential form of the Arrhenius reaction rate expression mandates that essentially the reaction rate is almost zero for almost all temperatures, apart from temperatures that are very close to the maximum temperature, okay? And so because we can write this, okay, then essentially we can say that this is the reaction rate at the maximum temperature divided by d omega by dt calculated at Tb, okay? And remember that the expression for omega t, okay, it's not equal, but let's say we're now interested in the dependence on temperature. So all we have to do is remember that there is an exponential dependence, okay, to the power of activation energy divided by RT, okay? And if you remember that the activation temperature was defined as a measure of the activation energy, we can say that omega t, okay, can be written as far as the temperature dependence is concerned, as minus the activation temperature divided by T, okay? Remember also the expression of the Arrhenius number, which remember is a high number, okay, for combustion reactions, okay? It's a high activation energy. Well, it's a measure of the activation energy, in fact. It's EA over RTB, okay, which can be expressed as TA over TB, okay? And remember, it's larger than 1. It's much larger than 1, okay? We estimated it between, remember, 4 and 60. So it's order 10 or more, okay? How do we express this derivative here, d omega by dt at this point? Well, it's pretty straightforward. If we consider this expression. So TA over T squared, e to the minus TA over T, okay? So let's continue here for our search for the expression for TB minus TI, okay? So it's essentially omega TB divided by this derivative calculated at TB. So essentially, this is equal to, well, we have e to the minus TA over TB in the numerator. And the denominator, we have essentially the expression for the derivative, which is TA over TB squared, and the same expression now for TA over TB. Note that over here, we were only interested in an expression which retained the dependence on temperature alone, only that dependence. But I could have added the dependence on, say, the concentration or equivalently on pressure, but this would have canceled out here, okay? So whatever dependence on pressure you have or equivalently in concentration of the reactants, okay, it cancels out. So essentially here you have an expression for TB minus TI, which is essentially TB squared over TA. Bear in mind that this difference is small, essentially because TA is extremely large, okay? And so going back to our expression of the gradient of temperature, okay? So in the reaction zone, remember this was TB minus TI divided by LR, so we can finally write down the expression TB squared divided by TA. Now we know all of them. We know TB, we know the activation energy, so the activation temperature, and LR. And the gradient of temperature in the preheat zone, on the other hand, was TB minus TU over LD. And so equating now the fluxes, okay, these gradients, okay, so TB squared over TA divided by LR is equal to TB minus TU divided by LD. Okay? And so we can sort of express the ratio that we wanted, which is the ratio of the thickness of the reaction zone to the preheat zone, okay? We can say that it depends on, well, generally TB squared, the full expression is divided by TB minus TU and then times TA here, okay? But we can write it in another way. We can write it as essentially TB divided by TB minus TU, and then we're left here with TB over TA. Okay. Let me rewrite this by dividing top and bottom by TB. So we have 1 over 1 minus TU over TB here. And here we have essentially the reciprocal of the Arrhenius number, okay, for this ratio here. So what the long story short, if you look at this quantity here, this is order 1. Why? Well, TU is generally, let's say, ambient temperature, and TB is the adiabatic flame temperature. So this ratio here is small, right? To the extent that if this is small, then the whole thing here is of order 1. Okay, so we can say essentially that the ratio, okay, depends on the Arrhenius number inversely. Okay, so that's one quite important result, okay, that the ratio of the reaction rate to the diffusive layer, so to the preheat zone, is inversely proportional to the Arrhenius number. And you know that the Arrhenius number is large, right? So for combustion reactions. So clearly, this ratio is very small. So this, yet again, another proof of the fact that reaction layers are extremely thin, okay? And they're confined to spatially localized, very thin zones. And the higher the activation energy or the Arrhenius number, okay, is, the smaller this reaction rate is. Indeed, this is a problem also numerically because in computational fluid dynamics, if you want to have a computer fluid dynamics program that really resolves the thickness of a premix flame, you need to have a very, very large resolution, so a lot of points, so that you can actually put sufficient number of points in the reaction zone and resolve, okay, the reaction rate. And think about the fact that the average thickness of a flame is of the order of a fraction of a millimeter. If you want to simulate, I don't know, combustion chamber of the order of 1 millimeter, sorry, of 1 meter, you need to have a huge number of points, okay? Which is extremely challenging, okay, in terms of computational power. Okay, that's an interesting result, okay, but which we more or less knew. Now we know that they actually scaled with the Arrhenius number, these thicknesses. But the principle and the main result that we really want to obtain is an estimate for or of the laminar flame speed. Now remember, the whole point of us doing a new or embarking in a new theory, the theory of laminar premixed flame, was that the Rankine-Hugoniot approach was totally insufficient for deflagrations. Okay, and especially it was yielding propagation speed of the CJ solutions that were way off, like 100 meters per second, which is ridiculous for a premix flame. It's too big. So we need a new estimate, okay? We need a new theory, laminar premix flame, and we need a new estimate of SL, okay? So how can we do this? Well, we have all the ingredients now. Again, remember the structure. So we have a preheat zone and a reaction zone, okay? So that's our LD, the preheat zone. This is LR, the reaction zone, okay? We have essentially a temperature which grows like this, okay? With essentially boundary values of the temperature, which are TU, TI, and TB. Okay, so look at this, let's say, one-dimensional representation, okay, of the flame. And well, beforehand, we expressed the continuity of fluxes. What can we express here as a physical, let's say, uh, first, um, the principle, let's say, that can somehow yield an expression for the laminar flame speed? Well, the most obvious one is the conservation of energy. Okay. So we take the preheat zone, and so let's concentrate on this area here, the preheat zone. Okay. The flame overall is adiabatic, so we don't lose heat or add heat from the surroundings. Okay. But if we consider this area here, there is a flux balance of energy that needs to be enforced. So somehow we should write for the principle of conservation of energy the fact that the inflow energy flux must be equal to the outflow energy flux, right? So let's see what the inflow energy flux is. So there must be an energy flux inflowing from here, okay? And this is a convective heat flux, okay? So let me write it here. So again, we're in the wave stationary frame, okay? So we're feeding essentially from this direction here, a mass flow at speed SL, which is exactly um, the flame speed, okay, which stabilizes the flame. And then essentially the energy would be essentially expressed in rho Cp and Tu, obviously because the temperature of the inflow here is Tu, okay? So this has the right units of essentially joules per meters per meter squared per second, okay? So it's an energy flux. So it's an inflow convective, okay, energy flux. Again, it's in joules per meters per second, per meter squared per second. So it's per unit surface area, okay, per unit time. So that's this arrow here. It's inflowing from here, right? What about another inflowing flux? Well, look at the reaction zone over here. Well, there is an inflow from the right here, which is, however, not convective, right? It's a conductive flux. So it's the heat flux coming from the hotter reaction zone, okay, that is heating up by conduction, okay, the preheat zone. So we will add, okay, a conductive or diffusive, if you will, inflow flux from the reaction zone, which is essentially conductivity and then a gradient of temperature, which is simply Tb minus Ti divided by Lr, right? So this is the inflow conductive heat flux from the reaction zone. Okay? Now we have to equate. Let me put this equation on the. Let me put this on the left-hand side. We have to equate this to the outflow, okay, energy flux. And well, the only outflow energy flux here is the convective energy flux, okay, that is exiting the preheat zone, okay, at the end of the preheat zone over here. So it will have this expression, okay, and then it will have this expression but a different temperature, which is the temperature Ti, clearly. Okay? So that's a principle of conservation of energy. Very, very simple one, right? We couldn't have done this in any way in the Rankine-Ogonio analysis because we essentially were not considering any form of diffusive thermal diffusion or diffusive heat fluxes, okay? So to start with, you can actually solve for SL and have some sort of expression. I don't know whether it's... We've also considered rho here constant in the reaction zone. If you, sorry, in the preheat zone, which is not a very good assumption. Okay, we're going to make a lot of those very crude assumptions. So some form of expression for SL, which is of this form here. So I'm solving from the above. So it's TB minus TI divided by TI minus TU, 1 over LR. Okay. Okay, so let us concentrate for a moment on this ratio here. Okay. How do we express it? Well, TB minus TI from the previous, okay, analysis was TB squared over TA. Okay. On the other hand, TI minus TU, we assumed it was very close to TB minus TU. Okay. So the ratio TB minus TI to TI minus TU, okay, can be written essentially as very simply like before, okay, TB squared over TA, over TA, TB minus TU, okay, and we essentially assume this to be approximately equal to the inverse Arrhenius number. Okay, so we have some expression now, which is of this form. One of the Arrhenius number and 1 over LR, which is not really useful yet because, well, because you can't really plug in LR, for example. You can plug in rho, lambda, CP, and the Arrhenius number because they are all, let's say, constants, okay, depending on the environmental conditions. Like rho, for example, will depend on pressure. Lambda and CP are properties of the mixture and of the fresh mixture, and the Arrhenius number is a property of the chemical kinetics, right? But what about LR? Well, first of all, let me just write down that LR, we just found out that it's LD times 1 over the Arrhenius number, right? And so if you look, if you use this expression, SL will be equal to lambda rho CP, which we call, this expression is essentially called the thermal diffusivity, okay? Lambda over rho Cp, and then 1 over the Arrhenius number, which cancels out because we can write LR as the Arrhenius over LD, okay? And so from this expression, you have the fact that the diffusive layer, okay, the premixed, sorry, the preheat zone, okay, can be thickness can be expressed as a thermal diffusivity over SL. Okay, remember the units the diffusivity is meters squared per second, and SL is clearly meters per second. Okay, so we have LD in meters. The preheat zone is therefore proportional to the diffusivity, thermal diffusivity. The higher the thermal diffusivity, the longer the preheat zone will be, because it will be heated up more, let's say, more effectively. But clearly it will be reduced if SL is higher, because you will have, it would be like squished, okay? You will have a higher incoming velocity to stabilize the flow, and so this gradient of temperature will be more squished onto the reaction zone. So you have this sort of dual effect: diffusivity on one side and the fact that SL can be larger. So think about this. It totally makes, so it's totally logical. Okay, but however, let's go back to our original problem. You can still see everything, right?
Sì, sì.
So let's go back to the original problem, okay? I want an expression for SL, okay, the laminar flame speed, that is actually useful, so that it's actually dependent on the operative parameters, okay, of my mixture. So I have, for example, one of the most important operating parameters would be pressure, okay? At what pressure am I operating this premixed flame, okay? So we have to get rid of this LR. Now, LR can be expressed as the laminar flame speed, okay, times some reactive time scale. I hope you agree with this, right? So that's one thing that we can definitely write. So let's see if I can really simplify things, okay? Okay. So let's see if I can estimate this, crudely at least, this time scale. Well, if you consider, okay, an n order, so the reaction order being n, irreversible reaction, for example, something like NA which gives P, okay? How do I write the rate of change of concentration of, say, A? Well, if you write it, for example, in terms of the mole fraction, okay, and for a moment you only concentrate on the dependence on the so we know, wait a minute, let me start from the beginning. So we know that the molar concentration will be essentially minus K, okay, and then the molar concentration to the power of n, right? So this is the reaction order. This is the reaction constant, which contains all the dependence on temperature, okay? So if we write down this in terms of mole fraction, okay, we essentially have minus K, the mole fraction to the power of the order, okay, of the reaction, okay, and then we are going to have a pressure to the power Pn minus 1. If you're not convinced that this is true, this is essentially, okay, the this product here is the dependence on the concentration of the molar concentration. Because if you remember, the molar concentration was a mole fraction by P over RT. Okay, and you can plug this in here, and this is what you essentially get. At this point, we're really interested in a dependence on pressure at a constant temperature. So we consider the temperature to be constant. So essentially, all the dependence on temperature is absorbed in this K here, in this constant K, okay? So to remind you, okay, the temperature is, we're essentially doing this at some temperature, okay? So how do we express tau R, okay? Well, you know that essentially X is a number which is from 0 to 1, so it's of order 1, let's say, okay? So this dx by dt is essentially the variation of x, okay, times delta t, okay? So this can be assumed as being something of order 1 divided by a reaction rate, okay? And this is essentially a constant which will depend eventually on temperature, okay? This quantity here, as we said, is something of order 1 to the power of n, and then a pressure to the reaction order -1, okay? Which is my essentially expression for the reaction rate, okay? So as you can see, the reciprocal of this sort of reactive time scale is basically the expression for the reaction rate, okay? But now the question arises, okay, but at what temperature should we calculate this characteristic reactive time? Well, that's pretty arbitrary, okay? So we can write down, for example, the highest temperature, which is the most logical choice, okay? So we assume T equals TB, okay? Although remember, this is pretty arbitrary because in fact it should be an effective temperature between the ignition temperature and the maximum temperature Ti. But for the time being, let's simplify things, okay? And let's consider the effective temperature as being TB, okay? It's a sort of a conservative choice, if you will. So this would be, using this expression, essentially KTB, and then, well, this 1 to the power of n disappears, and we have Pn minus 1. So eventually we have essentially an Arrhenius, okay, expression, minus Ta over Tb, and then a pressure to the n minus 1, okay? So we have some sort of expression for the reaction time, okay? So remember that we said that the SL, okay, the expression that we wrote down before, is a diffusivity, okay, thermal diffusivity, 1 over the Arrhenius number, okay, and 1 over Lr, okay? So this can be placed as, by substituting for Lr, okay, omega Tb over SL, okay? So this is my 1 over Lr, okay? So now let me rewrite this because there are 2 SLs here. So SL squared, okay, will scale, okay, be proportional to, let me consider this Arrhenius number really ineffective in the sense that this will be a constant, okay? So let me just get it out of the way. It's a constant that doesn't depend on the operative parameters, It depends on the kind of fuel, okay? So it depends on the kinetic structure of the combustive, reaction mechanism. And so it's something that is given. So suppose we're always considering methane, okay? And in combusting in air, okay? We know what the effective Arrhenius number is. So let me just take it out of the picture here. On the other hand, lambda rho Cp, you see that this rho will heavily depend on the operative parameters like pressure, okay? We're left with omega here, okay? And so we'll substitute p to the n minus 1. We use this expression, and then finally the exponent, the exponential here, Ta minus Tb. And this is essentially the part due to the reaction rate. So it's omega Tb. Okay? So this is a much more useful expression than the ones we've seen so far, because it really depends on two things. Okay? This part here depends on diffusion, okay, of heat. So this is a thermal diffusivity. In fact, it tells us that the higher this term here, so for example, the higher lambda is, the conductivity of thermal conductivity, the easier it is, okay, for the mixture to be heated up by conduction. So it's fair to say or to imagine that this directly impacts SL. And the higher the thermal diffusivity, the higher SL. Okay, because it's more efficient. The mechanism of propagation through conduction, okay, through the heating up of the fresh mixture, is more efficient. And obviously, this other part is due to the rate of reaction. So it's also intuitive that the higher the rate of reaction, the more effective or the more efficient the whole propagation mechanism is, because the higher the rate of reaction, the higher it will be, the higher the rate of flammable mixture consumption will be, okay? So you see that it will depend on several aspects of the reaction rate, okay? And we'll talk about those in a minute. So you can see that there are two, well, you can write them, two main, let's say, contributions to a cell, okay? Thermal diffusivity, okay, which gives us essentially the effectiveness of how efficient the heating up process of the incoming fresh mixture is by conduction, okay? And this is the reaction rate, okay? And again, both contribute positively, okay, to a cell. In fact, there is one last step, because if you look at this density here, we know that essentially the density, okay, if we use ideal gas law, is directly proportional to the pressure, okay? And so really what we can do here, we can substitute to this rho, we can substitute a pressure, okay? And if we substitute a pressure here, you see that this pressure here is to the n minus 2, okay? So the final expression will be something like this. Well, forget the square, we'll take the square root here. So we have rho divided by Cp, which is what is left of the thermal diffusivity sort of term. And we'll take the density, turn it into a pressure. So we have a P to the n minus 2, okay? And then the exponential, which is minus to the minus TA over TB. And this is our final expression. Okay? Is it exact? Well, no. It tells us the main dependencies, okay, of the propagation process of of a premix flame. Okay. So we have. Let me recap a little thing. So we have this first term here, which is essentially the effect of diffusive transport of heat. Okay. So again, heat conduction. In fact, going back to this other expression over here, you see that the density was at the denominator. This makes perfect sense because the higher the density of a gas, the harder it is to heat it up, to bring it to an ignition temperature. So we have to expect that if you're trying to propagate a mixture through a very dense gas, for example, at high pressure, okay, well, it's more difficult to heat up. So you see that the thermal diffusivity aspect is inversely proportional to the density, or if you will, to the pressure. It is not so for the reaction rate part. So this whole thing here, okay, is the reaction rate. Okay, the effective reaction rate. Well, in fact, the real effect of the reaction rate is only n to the -1. Now we've added this effect up back here. So this is the effective reaction rate and density. Okay, and clearly this will tend to increase the reaction rate, at least for an overall reaction order bigger than 1. Okay, and in fact, it won't depend on pressure if the reaction rate won't depend on pressure if the reaction order is identically equal to 1. We explained this in terms of the fact that unimolecular reactions, okay, in fact, don't depend on collisions, and therefore they're not totally dependent on how on the density, essentially on the on the pressure, and therefore on the density of the molecules, how close they are. So again, an effective heat conduction, okay, an effect of reaction rate and temperature. Look at also this term here, okay. Well, this is the adiabatic flame temperature, okay. So this will be directly related to the effect of the particular fuel and of the equivalence ratio. Because if you remember, okay, if we vary the amount of fuel to oxidizer, okay, well, if we have a lean mixture, we have a low value of, so this would be TB, and then a maximum value here, and then it turns to, and it decreases again for rich mixtures, okay? So off-stoichiometric mixtures have a lower adiabatic flame temperature because essentially the excess oxygen or the excess fuel will act as dilutants, okay? But if you have the perfect amount, then you'll express the full potential, let's say, or thermodynamic potential, okay? Okay. So this is more or less all of the dependencies. So one of the possible, questions that I can ask you is, how does SL, okay, the laminar flame speed, depend on, for example, pressure? This is the richer question that I can ask you, okay? How does it depend on pressure? Well, many ways, okay? So if we look at this, let's dependence on pressure. Well, look at this expression, right? So we had SL, which was depending on essentially two aspects, right? A P to the n minus 1, which was due to the reaction rate, okay, directly, okay? It's essentially related to the concentration of the reactants, okay? So as you increase the pressure, you essentially increase the concentration of the reactants. And we also had a 1 over rho, therefore a 1 over P. This was the effective density. Okay, it's harder to heat up if the density is high. So these are two ways in which pressure directly influences this expression, right? Clearly, the main effective pressure will affect the reaction rate. Okay, unless the reaction order is 1 again, so no net production of moles. Remember. So these two effects, if n is bigger than 1, generally it is. Okay. These two effects, the effective reaction rate and the effective density, are contrasting. Okay. Because on one hand, if you increase the pressure, you increase the concentration, you increase the reaction rate, and you make the flame faster. But on the other hand, it's more difficult to heat up by conduction because it's denser, okay? And therefore the two effects are contrasting, okay? Which of the two wins? Well, the net effect, okay, as you can see, the net effect is P to the n minus 2, right? Okay, the net effect of the density and reaction rate. So we have to understand, we have to know whether n, the overall reaction order, is bigger or smaller than 2. Because if it's smaller than 2, for example, for all composition, for all equivalence ratios, then we know that SL will decrease with pressure as a net effect. So you can evaluate the reaction order n experimentally. Okay. One thing you can do, for example, you can stabilize a flame, okay, a premixed flame, with a feeding a mass flow m, which is rho times SL. And we can use essentially for SL, the expression, actually, let me put here, say, scales like or proportional to the expression we just derived. Okay, so I'm only highlighting now the dependence on pressure. Okay, I'm not considering the dependence on temperature or the other constants like lambda and Cp. Okay, so you can take this rho inside, okay, and essentially you have the square root of rho and P to the n minus 1. And you see now that the mass flow scales essentially like p to the n, or if you will, p to the n divided by 2, p to the square root of p to the n. Okay. So what's the use of this? Well, it's an expression that essentially tells us that we can relate the mass flow, rho SL, okay, to the pressure and to the reaction order. So from this expression, we can write down that the reaction order is 2 the logarithm, natural logarithm of rho SL, okay, divided by the natural logarithm of the pressure. So you devise an experiment where you set the pressure and you vary the, or better still, for this particular pressure, you know what this mass flow is, okay, which stabilizes the flame, and then you essentially can estimate the reaction order. Now, this is the technique. Now, the truth of the matter is that for whatever equivalence ratio, actually, forget that. Oops. Okay, we can monitor and do an experiment where we always stabilize flames at different pressures. Okay, so we take a pressure here in atmosphere. Okay, and we measure the value of n. Okay, for all these pressures. Okay, and we have some sort of graph. Okay, at all these pressures. Okay. But the interesting aspect is that this reaction order is always less than 2. Okay, so the main experimental result is that the reaction order is always less than 2, even if we change phi. So we have an equivalence ratio. We can change the equivalence ratio. Okay, this is phi 2. It's always less than 2. Okay. And if it's less than 2, it means essentially that the general result is that SL decreases with pressure. Okay, that's one basic result. Okay, because again the reaction order, because SL, remember, scales like the pressure to the n minus 2. Okay, so if n is smaller than 2, obviously SL will inversely depend on pressure. Okay. Does it depend on pressure on any other, in any other sort of non-direct way? Well, if we look at this expression, okay, the direct ways were essentially the density, okay, at the denominator, which went up here. So this is an explicit dependence. But if you really think hard, look at this TB. That's the equilibrium temperature, okay? It's the adiabatic flame temperature. So it's the equilibrium temperature, the thermodynamic equilibrium temperature. Well, we know that the thermodynamic equilibrium temperature can depend on pressure, don't we? We've done many equilibrium calculations, right? In fact, TB generally can increase by a few percentage, okay, maybe 10 or 20%, if you dramatically increase the pressure, say by 1,000 or 10,000 times or something, okay? So it's not a very strong dependence, okay, but it's a secondary dependence, okay? Whether And you have generally an increase, okay? Well, if we have time, we'll try and explain that, okay? Later on. So just remember that there's a secondary dependence on pressure, because pressure will affect the equilibrium temperature, okay? um, well, we can skip this. I'll leave it as as an exercise. You can look it up on the you can look it up on the notes, okay? There's another statement which is in so we've used up the we used up the continuity of conductive fluxes, okay? Remember, between the preheat zone and the reaction zone. We wrote down a full conservation of energy, okay? What we haven't done is, for example, equate convective and diffusive fluxes, okay, at the preheat zone, okay, within the preheat zone. You can do that, and ultimately you will get an expression for the thickness of the diffusive layer, okay, at the preheat zone, okay? And it turns out that, so this can be done in maybe 2 or 3 steps, okay? And the thickness of the flame of the preheat zone, sorry, is has this expression, okay? So it will depend, well, on how effective, how conductive thermally the gas is, but it generally depends inversely on pressure. So it decreases, okay, as the pressure increases, okay? And again, this is exclusively due to the fact that as you increase the pressure, you increase the reaction rate. So overall, okay, the flame is essentially faster, okay, to complete the reaction, okay, as the mixture kind of flows downward, downstream, okay. So the flame in itself, this translates in a thinner flame. Okay, so this is something that I will leave as an exercise to prove this, okay? And you'll see that we have to use an independent physical principle, which in this case will be the equating the fluxes in the preheat zone, okay? The conductive heat flux and the convective heat flux and the conductive heat flux. Okay. I'm going a little bit fast here because I want to finish, because I think we can finish by today, which would be really happy. Would make me and especially you very happy. So, so let me just go back for a second to the expression of SL. Okay. Now, we talked about a lot about the effective pressure, the direct effect of pressure. Now let's concentrate on this term here, okay? So everything is a constant but this, okay? This is the adiabatic flame temperature. So let's look at the effect of the adiabatic flame temperature, okay? Now, in order to understand, well, you can see it directly from here, okay? As TB increases, okay, then this causes an increase in SL. Okay, it's directly visible from here. Okay. Now, the point is not so much this, which is pretty obvious, okay, because clearly, the hotter it is, the faster it will propagate. But what does TB depend on? Okay. And generally it will depend on three main factors. Okay. One will be the equivalence ratio. Okay. Another dependence will be pressure. We've seen that pressure plays a role in thermodynamic equilibrium. And I'll tell you why, okay? The main reason there is because as you vary the pressure at which the equilibrium takes place, you will vary the amount of dissociations, okay? I'll talk about that in a second, but dissociations are endothermic, okay? And so they will play a role on the final value of the adiabatic flame temperature, TB. And well, TB also depends on the molecule of the fuel. Okay, clearly, obviously. Now, if it's a hydrocarbon, it will depend on the ratio between the C and H atom. So it will depend on whether it's an alkane, an alkene, it's a saturated or unsaturated molecule. So this is the ratio, let's say, of C to H. Okay. Well, an obvious statement that we can make right away is the following. If you remember, we wrote that the adiabatic flame temperature is equal to the unburnt temperature plus the heat of reaction, okay? QC over CP. So it's pretty obvious that if you have a fuel with a high with a high QC, then you also have obviously high values of adiabatic flame temperatures and therefore higher values of the laminar flame speed. Okay. Oops. Okay, so let's look at this first point here. Okay, the role of the equivalence ratio on TB. So the first thing we know, you can do this by using any program like Cantera, for example. As you vary phi, okay, the equivalence ratio, you have, say, a peak around 1, okay, of TB. So when you have richer or leaner mixtures, the excess with respect to the stoichiometric proportion, okay, of either oxidizer or fuel will tend to essentially dilute the mixture. It won't burn, okay, so it will bring the temperature down, okay? And this is, let's say, the main reason, okay? Now, the truth of the matter is that in reality, if you look at this graph a little bit closer, okay, the peak of TB and therefore the peak of SL, okay, will happen a little bit on the rich side. So the peak is not exactly placed, okay, at the stoichiometric value, but it's a little bit displaced, yes, on the rich side. Okay. Now, why is this? Well, the short answer is here because on the rich side, okay, recombination reactions, which are exothermic, are more likely, more probable. Okay? I'll try and explain this intuitively. Okay? Now, if the recombinations reactions are more likely on the rich side, clearly, because they are exothermic, they will make clearly the adiabatic flame temperature higher. Okay. Now, the problem is, why are recombination reactions more likely? Well, what are recombination reactions? So essentially, you have to take the product, okay, of combustion, which is CO2 and water. Okay. Now, these both can either dissociate or recombine. Okay. And they will dissociate, well, CO2 will dissociate, for example, in carbon monoxide and oxygen. Okay? Same thing, dissociation from left to right, recombination from right to left for water into, for example, H2 and again O2. Okay? Now, when you are in rich conditions, okay, it happens that these reactions will be favored from right to left, so through the recombination side. So again, let me repeat this. When you are with rich mixtures, okay, with an excess of fuel, okay, then you are more likely to have these reactions occurring, so they will be more shifted towards the recombination side. Why is this? Well, because if you're, well, look at this, these molecules, okay? You have essentially C and H atoms, okay, that you need. Okay, and this comes, so these come from the fuel. On the other hand here, in order for these reactions to take place, you see that you only need 1/2, okay, mole of oxygen, okay? So this comes from the oxygen. So obviously the oxygen comes from the oxidizer, but you need less of it. So when you have a lot of C and H from the fuel and a little less oxidizer, these reactions will tend to be favored from right to left. And therefore, you have the process of sort of the exothermic aspect of dissociation recombination reaction prevailing. And that's why the peak is slightly moved towards the right. Okay, so this is a very short explanation. We would have to do it with chemical equilibrium considerations. Okay. Let me see if I have time. What about dependence on pressure? Okay, we did 3. This is from the equivalence ratio. What about pressure? So we want to understand what the dependence of TB from pressure is. Now, generally, TB, okay, will increase with pressure. Okay. And for a very similar reason as we saw before. The short answer is because, okay, endothermic dissociation reactions, okay, will be or are reduced, okay, at high pressure. Okay, so if you increase the pressure, you decrease the number of dissociation reactions, and therefore, because the dissociation reactions are endothermic, you decrease the amount of endothermic reactions that you have. And so the temperature goes up. Okay. Now you can we have all the means to see this also analytically. Okay. Oops. So let me simplify things to the core. Okay. Suppose that we have as a fuel, we have carbon monoxide. Now, carbon monoxide is not really a fuel. In fact, it is. It's part of what we call synthetic gas or syngas. CO still has to be oxidized to CO2. So you can consider this as being a fuel. In fact, it's one of the last steps, one of the last forms that the fuel, let's say, has before it's fully oxidized to CO. So this is for simplicity, okay? Otherwise, we would have to consider all the complex kinetics that occurs before, okay? Actually, the production, before CO is produced. But suppose you can still all hear me, right?
Sì, la sentiamo.
Yes, Professor.
Okay. So what's the last step? So the real fuel, okay, will do its own thing, okay? It will essentially dissociate in many different ways. It will be transformed in CO, then CO2, okay? So that's sort of the process of oxidation. So this last step will essentially be CO plus a half O2, okay, giving obviously the molecule of CO2. Very good. But now we're saying, wait a minute. Some of the CO2, okay, can be dissociated. So it does not exist in its molecular form, but it will dissociate. So suppose I have a very small amount, an epsilon number of moles, okay, of this CO2, actually dissociating back, okay, into epsilon moles of CO, okay, of carbon monoxide, plus 1/2 epsilon moles of O2. So I'm taking essentially this the other way around, okay? If I sum these two, okay, I have the following. So CO will oxidize, okay, into not just fully CO2, but in 1 mole minus epsilon CO2, because epsilon CO2 moles will be now dissociated into CO and oxygen. Okay, so this is essentially the overall what's happening. So you have essentially the final oxidation, which is not complete. You see, you have a small amount of dissociation. Okay, which we said it's epsilon. Okay, now keep this in mind. Now, suppose that I go back to my full oxidation, okay, reaction. I hope you remember how to write down the equilibrium constant, okay, from our studies of chemical equilibrium, okay, which is essentially partial pressure of CO, partial pressure of O2 to the power of 1/2 divided by partial pressure of CO2, okay? Now, this is for the complete oxidation, okay? But now, if we consider the final equilibrium composition, okay, with epsilon amount of dissociation, we have that the number of moles of CO2, okay, is not 1, but it's 1 minus epsilon, okay? The number of moles of CO will be, again, as you can see here, will be epsilon, okay? And the number of moles of O2 will be 1/2 epsilon. And clearly now the total number of moles, if you sum these three, will be 1 plus 1/2 epsilon. So we can write down the mole fractions now of CO2 because it's essentially 1 minus epsilon divided by n total, which is 1 plus 1/2 epsilon. And we could do the same thing for CO. Okay, I'm not going to do it, and O2. Okay? So take now this expression and let's use it now with an epsilon amount of dissociation. Okay? I will be very rapid here. Let's skip some steps. Okay, you can see them in the notes. Very straightforward. Okay. At the end of the day, you'll have essentially an expression of this sort. Some epsilon to the power of 3 divided by 2 times the pressure to the power of 1/2. So the bottom line is now we can express epsilon, okay, as some equilibrium constant, which only depends on the temperature divided by the pressure. So you see now to the power of 2/3. You see that the amount of dissociation epsilon now is inversely proportional to the pressure. Okay? So that means that as the pressure increases, you have less and less dissociation, and so the temperature will tend to increase. Okay? Okay, I've done it a little bit fast, but I've covered everything. There is a third. I'll give you 30 seconds to write down this. Again, don't worry about the fact that I'm skipping a few steps. This is just stupid, very simple algebra. I'm really interested in the final concept here, but I suggest you go back now and you really try and understand all the different ways in which SL, the propagation of a premixed flame, depends on pressure. So there are some obvious direct ways and some not so obvious indirect ways, okay? I will skip the third and final dependence, which is here, the molecule of the fuel and the ratio C over H, okay? But you can find it in the notes, okay? It's not too difficult to understand, okay? Did you finish copying?
Io sì.
Okay, if I switch to this, okay. Can you still see the blackboard?
Sì. Sì.
Okay. Okay, listen, I think we can close the course here, okay, which will make you very happy. I'm sorry that it was slower than expected, because it took me at least 3 or 4 lessons more than usual. I don't know why, but it must be the fact that I'm very slow at writing with the blackboard, okay? But we've covered the main aspects of premixed flames and the dependencies and everything. So now we have completed essentially the 3 parts, okay? Remember what we've done in this course. The first part was thermostatics or thermodynamics, okay? Done in a more modern way than the 19th century approach. Then we've done a very large sort of discussion on non-equilibrium chemical kinetics, okay? So the time evolution. And now we've more recently have looked at essentially spatial structures, okay? Flames and detonations and how they propagate, okay? Both in the detonation aspect and the deflagration aspect, okay? Now, if we had infinite time, I would be talking about non-premix flames, flames that have essentially the characteristics of having fuel and oxidizer segregated and diffusing into one another. And then once I would complete that, in part 5 would be turbulent combustion. I would add turbulence, okay, to our laminar flow, whatever turbulence is. But we don't have time, and you've got a life. So if you're interested again in doing a thesis with us, we will cover part 4 and part 5 in the thesis, essentially, okay, in a numerical way, sort of using computer codes, okay? Now, do you have any questions? We have 15 minutes in which you can ask me questions, not so much about maybe theory, but about maybe the exam. I don't know, just shoot. I know that hopefully this is my last ever lecture that I do remotely, so I'm pretty happy about this. Maybe you are too. So you're the 11 survivors of this course. I mean, we were a little bit more at the beginning. And so if everything is clear, we can close it there. But I'm sure some of you may have some questions. Let me just add one little aspect of the remote examination. Let's say the exam done remotely. Okay. Usually, if you know me, I'm always on the student side. Okay, I'm always trying to help in any way possible. But there is one way I cannot help. It's where you essentially take the notes, okay, remotely, and there is some way in which you can actually transcribe them in your written exam. Now, 99% of you will not do this, but experience tells me that there is a small number of students who tend to, for psychological reasons, tend to, to have the notes open, okay? Now, this is a written exam. Remember, this is written. Because if it's oral, I do this written because it's an English-speaking exam, so some of the students who are not familiar with the oral examination may find it easier to write, okay? But clearly, if you write down whatever is written in my notes, I will recognize that. And there is no way you can pass the exam, obviously, okay? What I would like you to do is what I would like to see written on the exam is your interpretation of the physical phenomena that I have tried to describe, okay? They shouldn't be one-liners or like, for example, I'll give you an example. If I ask you to derive the expression for the laminar flame speed, don't write down just the equation. Define your symbols, okay? What is omega? What is TB? What is TA? What is TI, okay? Otherwise, I'm not too sure you've understood what all these symbols are. But it should be compact. It shouldn't be like, you shouldn't write 2 pages of, writing, because that's useless, okay? You have, analytical tools and mathematics, which is very compact language, which is fine, but really do use words to describe what you cannot say with the language of mathematics, okay? I hope that's clear. So no notes, please, okay? If I always say, again, don't take it as a personal offense. 99% of you will never going to do this. But remember this: if I find a sentence which has maybe 3 or 4 words that I've used in the notes, one after the other, the chance of you using the same words is 0. Okay, 3, 4, or 5 in a row. So I will recognize that. Okay, since it has happened in the past, please don't do it because it's a waste of my time and your time. But other than that, most of you are excellent students. Well, all of you are excellent students, actually. But and we'll do an excellent exam where actually some of you are really excellent. I mean, I've seen interpretations of stuff that I've tried to explain that are actually better, much better than mine explanations. Okay, so sometimes that happened too, which is very rewarding, and it's very nice to see bright students like that. But on average, it's not a difficult exam as long as you. I will post now the full list of lectures with all the topics. Okay, so you know exactly what we've done. If you followed the course, not all will be in the exam, okay? Remember this. So try to study the main stuff that I told you was going to be in the exam. So, well, I won't repeat that, but you sort more or less you know what's going to be in the exam and not, okay? So are you sure you don't have questions?
Professore, solo una domanda tecnica sull'esame, ma le risposte possono essere date in italiano oppure devono essere scritte?
Come vi pare.
Ok, perfetto.
Certo, cioè se vi sembra, cioè se è più facile per voi, ovviamente sì, cioè non è un obbligo il fatto dell'inglese per lo studente, ci mancherebbe altro.
Va bene, grazie.
Ma qualche studente italiano ha deciso di, visto che il corso è in inglese, ha deciso di usarlo, di rispondere in inglese anche per esercizio, il che non è del tutto da buttare via, diciamo. Se uno si sente... I'm just talking about the Italian, for Italian students only now, if they can write in English or in Italian. Se uno si sente sicuro, abbastanza sicuro, è un buon esercizio. Questo lo ritengo. Però, insomma, potete fare tranquillamente a meno, Okay? We're going to be using exam.net. Well, wait a minute. This is an important thing. Now, exams are in person, right? So whoever is planning to take the exam in June or July, I'm going to be in the classroom, okay? But we still have the online procedure. For those of you who have requested the online procedure, essentially, okay? So you have to fill in a form, which was provided to you, which was given to you, and then you have to fill it in, okay? I will have a list of, so we'll do a mixed thing. So I'm going to be in the classroom, but some of you are going to be, so hopefully it works, I hope. Okay?
Scusi professore,
Sì.
ma relativamente all'esame in presenza si sa qualcosa sull'aula?
Nelle aule ho chiesto, allora il responsabile, la Colasanti, allora, voi come sapete, diciamo, le aule sono di competenza della facoltà di ingegneria, ok? Quindi c'è l'ufficio della segreteria della facoltà che se ne sta occupando. Per il dipartimento nostro se ne occupa Antonio Culla, professor Culla, al quale io ho chiesto, lui mi ha detto sto ancora aspettando. Noi cosa abbiamo fatto? Abbiamo riempito un modulo. These are all technical questions that have no, it's okay if I tell them in Italian, okay? Ho riempito un file Excel in cui ho scritto cioè il numero, diciamo, di studenti che mi aspetto, e in base a questo numero, ovviamente io ho molti meno studenti in questo corso che in quello di propulsione aerospaziale, ovviamente. In base a questo numero mi assegneranno un'aula, spero presto, perché se no... A quel punto io vi scriverò un'email in InfoStudio, ok? Tramite InfoStudio, in modo tale da dirvi, ok, ci vediamo alle 10 in aula X, ok? So, for those of you who are interested, who will take the exam in person, okay? Remember to do all the bureaucratic, procedures that you need to enter, okay? The facoltà di ingegneria in San Pietro in Vincoli. Vi dovete prenotare, I don't know, you have to book, whatever. And then I will write to you through InfoStud, okay, an email telling you exactly before the exam where the exam is going to be held. And I'm also going to write I hope very, very soon they're going to tell me what room they're going to assign us, okay? Is that clear?
Sì, però sì, il fatto è che noi per prenotarci appunto dovremmo
Bravo.
sapere l'aula perché ci dobbiamo
Geniale.
prenotare su ProDigit, quindi tutta la faccenda è
Scusate un attimo, ma
legata.
presumo che questo problema ce l'abbiate anche con altri esami. Mo adesso magari vi state concentrando, magari lei si sta concentrando solo su combustione, quindi non se ne occupa.
Sì, no, immagino che sia un problema per tutti, non
Io
solo.
non ho ancora ricevuto questa cosa, ma io mi confido adesso che è il 27, insomma dai, nel giro dei prossimi giorni sta cosa è molto difficile, assegnare le aule, ve lo dico, cioè è molto complicato, perché è un problema di coincidenza di appelli, ok? E di numero di persone, quindi devono fare un incastro perfetto, e, vi dico, è un lavoraccio, ci mettono settimane a fare cose del genere. Quindi cercate di capire il motivo per cui non lo stanno facendo, cioè, perché è proprio difficile. E non è detto che ci riescano, Se non ci dovessero riuscire, lo faremo tutto in remoto, che vi devo dire. Ok?
Va bene, grazie.
Se avete domande, scrivetemi email, io sono sempre disponibile. If you have any questions, write me an email, okay? And I will get back to you through InfoStud to communicate, the details about the exam, okay? Va bene?
Va bene, professore,
Allora,
grazie, arrivederci.
grazie a voi,
Arrivederci.
grazie della pazienza. Allora è finito il corso, eh? Forse comunicatelo a chi non c'era. Ok, lo scriverò comunque sulla classe.